going to talk here about the fact that how the Solow model can be formulated in either discrete time or continuous time. So we have the option that we can either model time as discrete or continuous when discussing the Solow model. So let's first look at the difference between discrete and continuous time. Now in discrete time, the variables of the model are defined only at specific dates. Usually it is defined as 0, 1, 2, 3. So time here passes in discrete intervals, and you can think of each period as a year or as any other arbitrary length of time. While in continuous time, the variables of the model are defined at every point in time. So in discrete time, you're only defining them at specific dates. But in continuous time, the variables of the model are defined at every point in time. So here time passes as a continuous flow. So t belongs to r here, real numbers. So here variables are only defined at specific dates. So here time is defined. So you have a t subscript with your variables, right? So when you write your variables, like for example, when you write y, you're going to write it with a t subscript yt. But in continuous time, time is constantly changing, right? Variables are defined at every point in time. It's passing as a continuous flow. Since time is constantly changing, it's not defined. So we do not have a t subscript with variables when we're modeling a Solow model in continuous time. So instead of using y with a subscript t, we'll just be using y, right? So in discrete time, variables are defined only at specific dates. Time is defined. So your variables have a t subscript. We'll write y with a subscript t, c with a subscript t. But in continuous time, the variables of the model are defined at every point in time. So time is constantly changing. It's not defined. We won't have a t subscript here. So here the notation we'll use will be, for example, we'll just say capital Y, we'll just say capital C. So now if we discuss rate of change in discrete and continuous time. So rate of change in discrete time is delta yt by delta t, which is just y, where delta yt is just yt minus 1, and delta t is t minus 1. Now t minus 1 is just equal to 1. So this simplifies to yt minus 1, which is just delta yt. So rate of change in discrete time is just simply delta yt, which is yt minus 1. Now if delta yt is greater than 0, yt will increase over a period of time. Now rate of change in continuous time is y dot. What is y dot? It's dy by dt. It's change in y with respect to time. Here it's important to keep in mind whenever you have a dot on top of a variable, it always denotes its first derivative with respect to time, right? So y dot just simply means the first derivative of y with respect to time. So this tells us change in y with respect to time. So this is the rate of change in continuous time. If y dot is greater than 0, then what does it mean? Y dot is greater than 0. This means that dy by dt is greater than 0. Change in y with respect to time is positive. So y will increase over a period of time. So rate of change in discrete time is just simply delta yt, which is yt minus 1. Rate of change in continuous time is y dot, which is dy by dt. It tells us change in y with respect to time. Now growth rate. So now growth rate in discrete time from year t minus 1 to year t is just simply yt minus 1 divided by yt minus 1. And in discrete time, we can also approximate the growth rate as differences in natural log. So gy, which is just yt minus 1 divided by yt minus 1, can be approximately written as the difference between the natural log of yt and natural log of yt minus 1. So this growth rate in discrete time is approximately the same as ln yt minus ln yt minus 1. We can look at a quick proof for this as well. We know growth rate in discrete time is yt minus 1 divided by yt minus 1. Now this is approximately the same as ln 1 plus yt minus 1 divided by yt minus 1 for small values of yt minus 1 divided by yt minus 1. So here we're using the approximation that ln 1 plus x is approximately x for small x. So here the x that we're using is this yt minus 1 divided by yt minus 1, because we're approximating that ln 1 plus this x is approximately the same as x, right? So we're using this approximation where x is just this term. And then if we simplify this natural log, then we know this will just simplify to ln yt by yt minus 1, just a bit of algebra. And then this can be written as ln yt minus ln yt minus 1. So using this approximation that ln 1 plus x is approximately x plus small x, what we can do is in discrete time, we can approximate the growth rate as differences in natural logs. So yes, so what we talked about was the growth rate in discrete time of y is just yt minus 1 divided by yt minus 1. And this can be approximated as the difference in natural logs. So this can be approximately written as ln yt minus ln yt minus 1. Now in continuous time, the growth rate of y is just y dot by y. Where we know what y dot is, it's dy by dt, right? It's the rate of change of y in continuous time. So we can now compute this growth rate in continuous time as y dot by y can be computed as the time derivative of the natural log of y. So what we do is, if we want to find the growth rate in continuous time, it's y dot by y, and this can be computed as d by dt ln y as a time derivative of the natural log of y. To see why this works, note that d by dt ln y can just be written as 1 by y dy by dt. Now, why is this true? Because look, we're taking the derivative of ln y with respect to t. Now, the derivative of ln y is just 1 by y, but we need to multiply with the derivative of the inner function. So we need to multiply derivative of inside. So inside is y. The derivative of y with respect to t is dy by dt, right? So this works because see, d by dt ln y is just the derivative of ln y with respect to t. Now the derivative of ln y is just 1 by y times the derivative of the inside. Inside is y. The derivative of y with respect to t is dy by dt. And dy by dt we know can be written as y dot. So this is y dot by y, which is just the growth rate of y. So what we're saying in short is the growth rate in continuous time is just y dot by y, which can be computed as the time derivative of the natural log of y. And let's look at a quick example. Say y is k alpha, and I want to find the growth rate in continuous time of y. So what we do is we take natural log on both sides. So this becomes ln y is equal to ln k alpha. And this alpha can be written as a coefficient of ln k using log properties. Now you take time derivative on both sides. D by dt ln y is equal to alpha d by dt ln k. We know the derivative of this is just, we know the derivative of ln y is 1 by y. Then you multiply with the derivative of inside y with respect to t, which is dy by dt. Similarly, over here, we are taking the derivative of ln k with respect to t. The derivative of ln k is just 1 by k. You multiply by the derivative of inside, which is the derivative of k with respect to t. So that's the dk by dt. Now dy by dt can be written as y dot, because remember we said we're using a dot on top of a variable to denote its first derivative with respect to time. And the derivative of dk by dt can be written as k dot. So if we have y is equal to k alpha, then we know using growth rates in continuous time, the growth rate of y is equal to alpha times the growth rate of k. So in continuous time, the growth rate of a variable is just simply y dot by y, which can be computed as the time derivative of the natural log of y.